So all right, so let's get started. So welcome back, everyone. So let's see. This is if you just came back here, this is so foundation of data analysis. So all right. So okay. So this is foundation of data analysis. I will. I still haven't posted the location of the TA hours. If anyone has any more thoughts on Zoom or in person, please. So please let me know. It was about a number of you wanted some Zoom office hours, so we'll at least do some of those. But if you've thought differently about that, please change. Please let me know. I will post those by the end of the week. And then all these lectures are also on Zoom, and they'll be on YouTube as well. There are people listening in on, so there are about 20 people on right now. So let's see. So the schedule, we did the first part of the class overview. We're going to start for the next two lectures a review of probability. These lectures will intentionally go fast, right? I'm trying to cover kind of review probability, just so we make sure everyone's fresh on notation and the meaning of these things. And in case you've had a probability class before, you probably should be fine. You might also be taking a probability class at the same time. That should also be okay. But these lectures will go fast. We'll try and cover roughly not everything, but most of the course in two lectures up to Bayes rule, and then we'll spend a little bit more time on that. And then there's going to be a quiz today. The first quiz 0, it's only worth a quarter of the amount of the other quizzes. It's mostly a practice for everyone involved, including us and the TAs, and hosting and grading them. It will be on Canvas. Yes. Oh, great, yeah. Good. All right. So good. So that'll be open until midnight, but I will be around. We'll have time at the end of the lecture at 10:45. If I haven't, 11:45, if I haven't stopped, please interrupt me and we'll give you time for the quiz. I'll be around for questions during that period, and also online for Zoom. This first one shouldn't take you very long. It's mostly about the syllabus. So okay, any remaining questions on the class organization before we get going? All right. All right, so review of probability. And so let's see. So the first thing to think about so probability is that we need to think of having a sample space. All right, and so this will be a space, and we'll often use a Greek symbol, so omega for this. All right, and this is kind of, and I'm going to kind of go through the mathematical definition. We'll go through examples. So this is a space of possible outcomes of some sort of event. So now, let's see. So and then you have a possible outcome. Okay, and we'll use a lowercase omega, and this will be, make sure I write this clearly, an element in the so in the sample space. And this is you do this in LaTeX, this is /in, right? So this is an element of, so if I use this symbol up here, it's an element of the space. And you also can have a, you can also have an event. Okay, we'll use an uppercase letter for this. This would be a subset of the space, of the sample space. Okay, so a possible outcome is one thing that can happen. An event is a possible subset of things. An event might be just one thing, but so an example here would be so if we like roll a dice or die, then the sample space, the possible outcomes are 1, 2, 3, 4, 5, 6. So we could have that the omega is equal to 3, right? And we could have an event, which is that it's odd, right? So then the event would be 1, 3, and 5. So if I rolled a 1, 3, or 5, it's everything is odd. Okay, and now so these so given this sample space, we can then talk about so probabilities. And see, there's a question. Oh, is stuff showing up on Zoom, Ian?
Yes.
Oh, okay, good. So then you can talk about a probability of an of an event, and we'll get into kind of other ways of thinking about this. But for the first thing, if everything is equally likely, then we'll write the probability of A was going to be the size of the event A over the size of this like the sample space. If I have a set notation, yeah, just to review, this is like a set notation. I have these curly brackets, right? This is a set. There's not order to them. If I want to say the cardinality of the set, I put two bars around it. So this would be the set 1, 3, 5 over the full sample space 1, 2, 3, 4, 5, 6. And this is 3 out of 6 equals 1/2, right? So if you roll a die, probability 1/2 is going to be a number which is even. So great. So slightly more formally, a probability is so of an event. Again, we're going to use this this probability of this event A as the notation. So it's going to satisfy 3 properties. 0 less than equal to the probability of A is less than equal than 1. So it has to be in between 0 and 1, the probability of some sort of event. Okay, the probability of the entire sample space has to equal to 1, right? So the chance of any possible outcome, it has to come from the sample space. So if I so that has to go to 1, and then let's see, and then I have to have this kind of this last property, which is if I have a sequence of events. Okay, let's say these are A1, A2, and so on, that I have for I not equal to J, that the intersection of I and J is equal to the empty set. Okay, that means you can't see that, can you? The intersection of those two things is, put it up there. So the intersection of these 2 events is empty. That means they can't occur at the same time. Okay, so if I have this property, then I can say that the probability of the union of all of these events is equal to the sum of the probability of these events. Okay, so think of a way of thinking about this is I've got some sample space here. And then within the sample space, so I'll think of it as filling in this area here. Okay, and I've got this event A1, and then I have A2. Okay, and these do not intersect with each other, right? So this is A1 and this is A2, and they don't intersect with each other. And then I've got A3 and A4, and these aren't intersecting. Okay, so now I can think of the probability of this area as like throwing a dart in this, and it has to fall in the sample space, right? So anywhere I throw a dart, it has to fall in there, and it's going to fall into one of these events. If I fall into A here, then it's going to be A4. This is the possible outcome, right? And so it's inside of A4. But I can't have more than one outcome, more than one event be true at the same time. And so if I look at the union of all these things, right? So I look at some total region, let's say this region defined by all of these events together, that the probability of it falling in that whole yellow region is the same as the sum of the probabilities of so all the pieces. Okay, so these are the three. These are the three kind of key things you need to make up a probability. Okay, you need these three kind of properties to be true at the same time. So okay, so let's see. So as an example, here you can think of having a biased coin where with probability of tails, we can say the probability of tails equals 0.4 and probability of heads equals 0.6. Okay, if you have a coin, you can't get heads and tails at the same time. Okay, and the total, you either get heads or tails, so the entire sample space is heads or tails, right? And the probability of the total sample space is 1, and if I add up the probability of heads and the probability of tails, I also get 1. Okay, so this kind of, everything I said checks out. Okay, good. It's, the definition is a little bit more complicated. These sets, the sequence can go to infinity and all this other stuff. We're not going to worry so much about those details here, okay? All right, but if you have any questions, again, please ask. There are more questions in the chat. Oh, is that everything still showing up? Yeah. Okay, great. Okay, great. Okay, so these are kind of discrete sample spaces. There are also continuous sample spaces. Okay, and if you have taken actually, if you took a probability class at the U that wasn't in the math department or was not in the CSEC department, you actually didn't talk about continuous sample spaces. Which seems odd to me, but we'll actually need these ideas will be very useful. And so these are important when the quantity we're trying to understand is not like a discrete quantity. Like if you roll a die or flip a coin, it's going to be very discrete. But you can have other quantities like measuring time, kind of water, like during the rain, that big rainstorm last week, it rained like something like 1.5 inches on campus within a 24-hour period. I guess there's some place out in the West Desert got like 5 inches in like 24-hour period. That water, but it's not exactly 5 inches. It doesn't go from 4 inches to 5 inches. It goes in this continuous kind of trickle of, I guess they're raindrops, but each raindrop has kind of a quantity to it. If you do spatial things like land, these are all continuous quantities, right? So we want to define probability over these quantities as well. So an example would be, let's see, if we're supposed to start class at, let's say it starts at 10:45. Okay, but 10:45 is not, and yeah, I guess it's an exact time, with 0 seconds. Now, I guess I didn't start even at 10:45 today because of technical difficulties, but I could have started at 10:45 and 59 seconds, and I would have still said I started class on time. Okay, it still would have been before it was 10:46. There's kind of this continuous kind of range in between here. Okay, and now this is where it's really important to think of these events instead of these actual outcomes, because a particular outcome is not actually going to have, the specific time is not going to have an actual, no, it's hard to quantify the notion of probability. In fact, it won't have a notion of probability. We'll have something called a likelihood, which we're going to use. But so instead, let me get another dark color here. Okay. Instead, you can think of an event that I'm probably not going to start at the very beginning. I'm going to start in the region, some event, which is the time 10:45 and 20 seconds through 10:45 and 59.99 kind of seconds here, right? If I do this, I'm still starting on time, but I'm not too eager to start the class right exactly at 10:45. So this is, this is an actual event. It has a continuous and infinite set of possible outcomes it's containing, and I can say that the probability of being of starting within 10:45, but not right at the kind of at the first 20 seconds of it, might be something like 0.75, right? Even though this is 2/3 of the time window, the probability does not need to be so uniform. This is 3/4 of the probability I'm starting a bit late. Okay, so I can talk about probability over continuous events in these ways. Okay. So great. So we can have these continuous sample spaces as well. All right. And as I said, hopefully this isn't going too fast for everyone. Hopefully this is mostly review, or if not, this is at least making intuitive sense. Okay, so the next very important concept is a random variable. Okay, and okay, so a random variable is probably maybe one of the trickiest concepts to really kind of understand what's going on here. So in a kind of in a technical sense, it's kind of some function between two sample spaces. Okay, so you would write this as x from some sample space. This is an uppercase, so lambda. I think these are Greek letters. If you can't tell, 2 are usual sample space omega. They're both, it's a function from the sample spaces. And the idea is that I don't know what's going to happen when I define this function to talk about it. I don't know what's going to happen in lambda, but I know when it happens in lambda, I know how to map it to something inside the magnet. Okay, so you can think of it as a kind of computer scientist. You want to think of it as a variable that has not yet been defined, or maybe not, it hasn't been defined, maybe it's been defined, but I haven't given it a value yet, or not so given value. But it's kind of more interesting than that, in that, I mean, I think of it about it as I'm going to read the outcome from this sample space, and there's some function that defines it, and I'm going to get some sort of input, and I know what the mapping is going to be. So I can think of it actually, you can think of it as a variable that has not yet been defined. You can think of it as, and maybe that's the outcome of some function, right? So I can think about, there's some omega here, which is from a function x, which takes in this lambda, and I don't know, I do not, so no lambda here. Okay, so I have a well-defined function, which I've written in a program to do, and it's going to give me this value omega, which is going to be an outcome. Okay, but I don't know what this outcome is yet because I haven't figured out what lambda is. Okay, and then we can kind of often we put like a uniform distribution over some range of what lambda is. It doesn't have to be uniform. You can chain these together in various ways. But, and then that gives you, then you can talk about the distribution over the values of omega. Okay. Yeah, question.
So I followed you all the way up until here.
Okay, yeah.
Can you give an example?
Yes, yes, good. So let's give yeah, great. So I'm going to give an example with a coin again, but I'm going to get points out of the coin. So if I'm going to have a coin with points, okay, now my initial sample space, which I'm starting from, is going to be heads or tails. Okay, so I'm going to give a heads or tails, and you can think I could put this is a fair coin, right? So I could say something like implicitly probability 1/2 heads, 1/2 tails, but that doesn't matter so much. What's more interesting is the points here. Okay, the points are going to be 1 or 4, as it turns out. Actually, I can say the points are going to be some real values, and there's going to be a random variable. Yeah, these are the real numbers. Okay, so there's some random variable which is mapping from heads or tails to these points that I'm getting, and in fact I can define this that for heads I'm going to get a value of 1, and for tails I'm going to get a value of 5. Okay, so now I say that if I get a heads, I get 1 point. If I get a tail, I'm going to get 5 points instead. Okay, and so this is the random variable which is mapping from one sample space to some different sample space, to some outcome. I'll talk about things, and we'll kind of get to this. I think, we won't get to this till next lecture actually, but I'll talk about the expected value of a random variable, right? Say, what is the expected number of points I get? Okay, and so this notion of random variables and this function and kind of mapping from a sample space to an outcome, this is needed to talk about expected values and covariance and all this stuff, which will come up throughout the course. Great. Okay, it's a simple example. Yeah, these kind of notions of random variables, again, this is one of the things I'm mentioning that, and it has a very formal definition in mathematics, right? So it used to be up until, I guess, maybe like 30 years ago, that to teach a probability course, you would need to go through like all of measure theory to do it, right? And then they realized, well, probability is too useful and not everyone wants to go through all of measure theory. But the true definition of a random variable is from measure theory. But when it's often taught, it's taught as kind of, well, there's something about this function that has to be like a measurable function, and all this other stuff, and that's kind of brushed under the rug a little bit. But it's kind of this way of converting from one sample space to another. And so useful when I don't know, kind of there's some event, some input, which I'm going to be taking. Like you have a computer program and you and you can get input from a user. They can press radial buttons or they can type something. You don't know what they're going to do. But you can map it to some outcomes, okay? If I do have a knowledge in some probability sense over the heads and tails about what the user might do, say it's enter your name or like your age or something like that. I might have a probability distribution over your ages. Then I can say something about what the outcome of that function is going to do with the random variable. It's a way of kind of converting from one sort of input to a different sort of input. And when we talk about randomized algorithms, and we'll do some randomized algorithm classing. Aren't going to be very hard, but like quicksort is randomized. But it'll be kind of a different way of thinking about it. Then the randomness will come from inside the algorithm. In other cases, the randomness will come because we're modeling the data in some way as being random from some unknown distribution. And we're trying to learn about the distribution the data is coming from. Okay, so these random variables allow us to talk about these processes. Okay, but in the nice thing about these random variables is that we can kind of treat them like variables we would inside of algebra or inside a computer program. We can do things like we can add and subtract them and stuff like that. So we'll be using them in that way, and it's representing some unknown outcome, but we can talk in some sense about probability with respect to it. So I will talk about random variables within other contexts, and hopefully this will help make things a little bit more clear. But you know, if it's not clear at the end of this lecture, then I'll review it at the start of next lecture. I know this is, as I said at the beginning, this is one of the more confusing concepts within probability, but it will feel natural once you get using them. It's a really useful abstraction here. The next thing I want to talk about are conditional and joint probabilities. Okay, so this is where I'm going to have two things happening at the same time, and I'm going to talk about this from two perspectives. One is events, and one is again from these random variables. Okay, so think of first I'm going to have two possible events, A and B. For events, I'll typically use events I'll use uppercase letters, usually from the beginning of the alphabet. And random variables typically from the end of the alphabet. Often X is used. Okay, and so what's important here is this notion of conditional probabilities of A conditioned on B. Okay, and so this has kind of from a mathematical form, we can just write that this is A intersect B. That means A and B both happened, divided by the probability of B. Okay, so this is, so these again, remember, these are sets, so I can take intersection of the sets, right? So if they take an intersection of the sets, that means that they both happen at the same time. So with heads and tails, these are now sets that are potentially intersecting. Think of a die I rolled, it could be an even number, and it could be one of the first three numbers. It could be 1, 2. So I could have A equals 1, 2, 3, and B equals 1, 3, 5. And the intersection, then A intersection B is 1 and 3. right? Okay. What I find is kind of a visual way of thinking about this is that, again, I've got my sample space. Okay, this is my entire sample space here. And I think of an event, again, I think of this event as A, okay? And it's some subset of this sample space, and I could have another event here, B, okay? And so now the intersection of the two is going to be purple, right, in here, and only if I get kind of a, one of my outcomes inside here is it in both A and B together, right? Okay, what is, I think, more helpful, and this is where it helps to draw it as a rectangle, is I could think that there's some these kind of the I could have that A, let me write this way, that A is defined as kind of a vertical strip. Okay, so if A is defined as a vertical strip and B is defined as a horizontal strip, so let's say there are different things happening. One is saying a quantity that has to do with A, has to do with someone's age. Their age is between 19 and 21, and the B is the grade point average, and let's say the grade point average is between 0 and 4, right? And there's some range which encapsulates A and B each. Okay. Let's see. Okay, so let's say that A is going to be this range, and B is in here, and you can see that there's some set which is intersecting A and B. Okay, so then there's some range in the middle here. Which is kind of A and B. Right, this is a intersection B. Okay, that's both of these happening. Okay. So now that these are two events happening, there's two different ways that it could happen. This is kind of a nicely structured way. This is kind of a more abstract way. And now let's think about this conditional probability. What is happening here? What the conditional probability is saying, I'm going to look at the probability that A is true, given that I know B is true. Okay, so this is probability of A given I know B is true. Okay, so now I'm saying I've somehow get some extra information. I know I switched the colors here, didn't I? Okay, that's confusing. So let's say that I know B is true. So I know it has to lie inside of this kind of this region. It has to lie in here. So I can kind of take my eraser and I can get rid of this part here. Okay, I can say this part did not happen. Maybe I shouldn't have erased it so much, but okay. This is still A, but now this region here, now my sample space has been restricted to B. I know it has to be restricted to B. So I can kind of think of having a sample space restricted to B here. And now I can say, what's the probability of A restricted to B? Well, it used to be, I could think of the probability of sample space was 1, right? It was always in the sample space. But now the probability of sample space is kind of smaller. I'm restricted to B. Maybe this happens 40%, B happens 40% of the time. So I need to take the probability that I landed in both, but then divide it by, say, 0.4, right? So if this value is equal to 0.4, now I'm dividing by something less than 1, right? And so if this value here was 0.1, well, then I get 0.1 divided by 0.4, that's 0.25. That's a probability again. Okay, it's still a probability because the intersection of A and B has to be less than B, right? And these are positive quantities, right? So this is still a valid probability, but I'm restricting to the space. Okay, so there are two examples here that I've drawn. Okay, so this first one is a nice example, and I'll define this formally. This is independent. These are independent random variables. This one is not independent. Well, it's not necessarily. I think they're not independent. If I could restrict to B in this case as well, okay, I could say what's the probability that I'm in A and what's the probability restricted to B? So I'm kind of blocking out, ignoring the rest of the sample space. Now the probability I'm in A given I'm in B is only these small magenta regions. Okay, so it's restricting that sample space down to knowing it's in B, and then I take the probability of everything that's left. That's another way of thinking about this conditional probability. Okay. Okay, so let's formalize this notion of independence. Okay, we say two events A, B are independent if and only if the probability of A given B is equal to the probability of A. Okay, so if I look back at here, the probability of A, I said this one was a dependent case, the one on the right here. The probability of A does not change when I restrict to B, because it only depends on, think of this, A only depends on the X coordinate, right? How far left and right I've gone. Where with B, so when I restrict the Y coordinate, well, it doesn't have any effect on the X coordinate, right? So these are independent of each other. Restricting to B does not change the probability of A. That means that your age and your grade, for instance, in that example, did not have any effect on each other. Okay. Whereas in this case, it might have an effect. These are the case on the left, this kind of more general case. These are kind of these things that depend on the domain in some less controlled way. And if I restrict to B, the probability of getting A probably actually goes down here. It might be that in this case, I might have that the probability of A is equal to 0.2. So this is 20%, but the probability of A given B might be something like 0.1. Only 10% once I've restricted to B, the probability of falling in A is smaller now, right? So this was not independent in the case on the left. Okay. Okay. Let's see. I'll go through another table example in a minute, but let me say there's another notion of independence for random variables. Okay, so we say did I write 2 that way? Let me fix that. 2. Okay, so I'll say 2 random variables. And now I'll say, call these X and Y are independent. And now I have to say if, so these random variables, so I'm going to have, so I'll say that X can go from some domain X to, and let's just say it goes to the real numbers, and y goes from some domain y to the real numbers. And so, and I'm going to, actually, I want the outcome sample space. Sorry about this. We'll often talk about random variables with just the outcome sample space in mind. And it's possible they're the same, that they're both real numbers. Okay, so I have two outcome sample spaces, and I have, so this is true if for any, let's say any or all, let's say for all events A as a subset of X and B as a subset, B is a subset of the sample space. So why that A and B are independent that in the events A and B are independent of each other. Okay, so I can define the probability over these events, and I want to say for the random variables are independent if for any possible events that I'm considering in the output of these random variables, if those are going to be independent of each other. Okay, so I need to be held for any events that I'm considering. And so this is a stronger property because this is possible, because it's it's over these functions that could map in different ways. Okay, so we'll see kind of some, I think later we'll see some examples of this. Okay, okay, so let me go through another example of, so these conditional random variables. Okay, so one way of expressing kind of this joint probability is in some table. Okay, and this will be a simple discrete example we'll start with. And then I will talk about some continuous examples where it's going to be more easy, more important to talk about these random variables. But right now we can just talk about these events. And I'm going to talk about two events. So let's say someone was exposed to a high dose of COVID, right? So they interacted closely with someone who had high viral load, and then there are going to be two cases that they are, so are they vaccinated or are they not vaccinated? Okay, and did they get severe COVID, or did they get no or some mild COVID? Okay, so these will be the two outcomes. This I'm going to say is going to be C equals 1, and this is C equals 0. Okay, so these C's and B's here are going to be I'm going to use these as these random variables. There's some underlying process going on here. And someone was either vaccinated or they were not vaccinated. That's the outcome of that's, well, okay, no, I can just treat these as, yeah, and then the random variables map to a sample space of 0 and 1. Okay, so the outcome sample space of the two random variables 0 and 1. The random variables will hopefully make a little bit more sense once we get to the continuous examples next. So the two outcomes are 0 and 1 for the vaccine. You can treat these represented this way. And getting severe COVID or no and mild COVID is also 0 and 1. Okay, and I'm going to write this as a probability table. So what that means is I'm going to write all the joint events. Okay, so if I got COVID and I had the vaccine, so I'm going to say that this happened 1% of the time. I did not have the vaccine and I got severe COVID, that's 20%. I had the vaccine, I did not get severe COVID as 54%, and had the vaccine and did not get the vaccine and did not get severe COVID as 25%. Okay, so I can think of this as a larger sample space. I can think of this having a big sample space if I want here, which is going to be C equals 1, V equals 1. That's one element of the sample space. C equals 1, V equals 0, C equals 0, V equals 1, and C equals 0, V equals 0, right? I can think of it as these four elements in here in the table, or I can think of them just based on the C or just based on the V, right? But the four elements in the table, this is an outcome samples. This is a sample space. And so it satisfies the properties of a probability. All the possible events have a probability between 0 and 1, right? The blue numbers there. If I add all these events up, they should, if I did this correctly, these should add up to 1, okay? And I can also talk about things like I can derive from here the probability that someone got the vaccine. In the US right now, I tried to do this, it should be 0.55, right? That's the sum of these two elements in this column. I could do the same in a row. You get the probability of getting a severe case of COVID, that might be 21%, 0.021, okay? Then I can do something, start to do some things more interesting. Let's see, probability that I got a severe case of COVID, given that I got the vaccine, okay? So now what I do, it is the joint probability that I got severe COVID and the vaccine is here. So this is the probability of C equals 1 and V equals 1 divided by the probability of having the vaccine, which we already calculated. And so the top one is getting them both, and that's 1% divided by 0.55. And so in this case, it's about, it's about 0.19. Sorry, 0.019. 0.19, so almost 2%. I got a very big exposure from someone, then I might have a roughly 2% chance, given that I had the vaccine. Okay, given I had the vaccine, this is something I know. So then I can restrict my probability to that case, and now I can figure that out from the table. Yes.
So does that notation mean the probability of C equals 1 or V equals 1 or C equals 1?
This is a probability of C equals 1 given that V is equals to 1 is true. So given that I have the vaccine, what's the probability I get a severe case of COVID? Okay, that's what this is saying. Yeah.
Could we go back to your definition of independence with, I'm just a little confused.
Yeah, we'll talk about that in a second in the example. Yeah.
Okay,
Yeah, so here's, I was going to say that I should have said for independence, this is, I forgot to write something on this slide. This is also true that B given A is equal to the probability of B, and that the probability, you also get the property that probability of A times the probability of B is equal to the probability of A and B being true. You also have these properties. These are equivalent you can get by algebraic manipulation. If I expand this, then I get this fraction, and I can divide, and I can get these other things. Okay. Okay, so let's look at this example with independence here. Are these two events independent? Okay, so are getting a severe case of COVID independent from the probability of getting the vaccine? To do this, the first thing I want to do is I want to calculate the probability that I get, not knowing whether I had the vaccine, that I would get a severe case of COVID. This is equal to 0.01 plus 0.2. right? So this is 0.21. Okay, so this is, and if they're going to be independent from each other, then I need to say whether the probability I get COVID, is this equal to the probability of C equals 1 given that I got this vaccine? And these are not equal to each other. Okay, so these are not independent. Okay, so they're not independent. Is this a good thing? Would I want these to be independent?
No.
No, right. Yeah, that means the vaccine is effective, right? And so this is the basics of how they've kind of done trials about populations, and they kind of make sure that they line up the demographics of people, and then they say, oh, the probability of getting COVID is way smaller if you have the vaccine, you know, so we should give everyone the vaccine, right? That makes a lot of sense. And it's true not just for mild severe, but a bunch of other properties. And then with the announcement on Monday, they finally said, yes, and we're willing to verify that it's safe, right? And hopefully the Moderna just turned in all their paperwork apparently. So hopefully that one will be given the same proclamation soon. But okay, so here's an example with independence. Is that what you're hoping to see?
Yeah, I was kind of more wondering as well with like two just disjoint sets, whether or not they're independent or dependent. Because with that definition, it seems like they would get, like logically they'd be dependent, but they wouldn't based on that.
Yeah. So let's look at it just with the picture. I think a picture will help kind of you understand what is going on here. Okay, so these are two independent sets. Okay, what is the probability of A is equal to, let's just pick some number, 0.2. What's the probability of A given B that's equal to the probability of A intersection B divided by the probability of B? I don't even need to know what the probability of B is. What is the probability of the intersection? 0, right? So if they're disjoint, the conditional probability is always going to be 0. So unless A cannot occur, right, then it doesn't have any mass at all, then these are not going to be independent. This is a very strong way of them not being independent. This would be like saying, if I got the vaccine, I could not get a severe case of COVID, and they would be completely disjoint from each other. That's not quite the case yet. With the vaccines, they are like amazing marvels of medical science, that they're as effective as they are, but they aren't quite this effective. Yeah, but this would be a very strong form of dependence between these events. Okay, let me start a little bit here on density functions, and I think this might help with the notion of random variable, and then we'll start the next lecture going over these again. Okay, so with the density function, this is something where I'm going to have how I deal with continuous random variables for these sort of things. And instead of writing down a table where we can do some simple calculations, some simple algebra there, we have to deal with calculus and all sorts of stuff. And this is why these aren't taught for a bunch of the campus, it turns out. Okay, so the idea is we're going to have some random variable x, and with that, we're going to kind of have with it we're going to explicitly define a function f of f so sub x. Okay, and so this function is typically will go from the real numbers to the real numbers. Okay, and example of this function, we might think about this as this is 0, so this is the real numbers, and we're going to see something like this. This will be kind of looks like a Gaussian, like a one-dimensional Gaussian. We'll talk about these in higher dimensions a lot in this class, it turns out, which are pretty simple to work with, but it's the same thing as a normal. A one-dimensional Gaussian is a normal distribution. So it's got a mean of 0. And so there's some other height function here, which is the output of this function f, right? This is, so this curve here is the function f of x, right? And so this is also real values. And if I have it so it's kind of a standard normalization, right? Well, like this is the scale, then the height here is about 0.4. Okay. So this is kind of one of these functions. And so I get this function f, I get a value on the axis, a value, and it maps. And so I'm going to think of this guy now in this kind of more mathematical notation of 4. This is lambda, and this is going to be omega. These are the sample spaces, right? So if I have a value lambda, it's going to give a height function that's going to correspond with the mega here, right? So this is a function, a continuous function, can correspond with the continuous random variable x. Okay, and what this is one way of thinking about some sort of random variable, and in this case, it could be this other way where I get points. There's a much more general way of thinking about it, where I can use them in a more general setting, and we'll see them throughout the class. But it tells me kind of if x has this distribution, that the probability of getting kind of tells me something like the probability of getting this value lambda. Now it's not a probability. The probability of getting of x, I can say the probability of random variable x becoming, okay, so you often write it this way, that the probability of x is equal to lambda. Well, you would say, is this going to be this value here, omega, about 0.3? Now, it turns out this is 0. I can't actually say a probability here, but what I can do is I can identify some region, say between, say this is A. I'll just say this and then we'll get to the quiz. This is the region between 0 and 1.2. And I can say this is well defined, that the probability that you just say of A, or you say this is the probability that x x is in A, and I can say that this would then be, I have to integrate over this region here, right? So what I do is I take this and I integrate over this region. What is the area under this curve? And this gives me some probability. It's the area under the curve defined by this event here on the x-axis. Okay, and so this will be something like, this might be 0 point, let's say 35, something like that. Right, so I can talk about probability of a region of a continuous random variable. Okay, and we were going to actually use Gaussians and kind of random variables in this way in the future. So I will go over this again at the start of the next lecture. So great. So we'll stop. We're stopping class, the lecture a little bit early because I'm opening the quiz. The quiz should now be open. Just a reminder, this is a quiz on the syllabus. And I think I said in class on Tuesday, you can use the syllabus on this quiz, but do not talk with other people. It should not be hard. Just please go and try, and I want you to answer these questions. You're welcome to do it here, and I will answer questions in the classroom, and I'm going to have the chat open. Okay, but I'm going to try and turn off the YouTube at this point. Okay.